In this video, I want to take a look at solving separable differential equations, and particularly those that have an initial condition so I can find a particular solution at the end. These are also called initial value problems. So in order to be separable, this means that I can separate my x terms with my dx on one side, and I can separate my y terms with dy on the other side of this equation, and I can integrate both sides. Okay, right now it kind of looks like they're all jumbled up. So let's start by taking this y prime and making it a dy dx, and that'll kind of give us a better idea of which way I should go to get these things separated. Okay, so this dy dx, my dy is in the numerator and my dx is in the denominator. So I know that my y terms will be on the left with my dy. So I'll need to multiply both sides by dx in order to get this dx in the numerator, and that'll be so on the right side. So that means that my x terms will need to be on the right and my y terms will need to be on the left. So this is where I am right now. So let's go ahead and do some division. I'm going to need to divide by the square root of x squared minus 1, and those will cancel. And I'm going to need to divide by y as well, so those will cancel. And I've done this so I can go ahead and get all those y terms with my dy on the left and the x terms with my dx on the right. So once I separate all this stuff out like this, I can go ahead and take the integral of both sides of my equation. So that means on the left side, I'm doing the integral of 1 over y with respect to y, which will give me the natural log of the absolute value of y. On the right side here, it looks like in order to facilitate this integration, I'm going to need to use a U substitution. So let's go ahead and use the U, the expression that's underneath that radical. So U equals x squared minus 1. So du equals 2x dx, which means then that dx will be du over 2x. Okay, so let's go ahead and take a look at the substitution. So I have a 10x on top with the square root of u, and my dx becomes du over 2x. And I'm going to have some things cancel here. These x's cancel, and this 10 becomes a 5 while this 2 becomes a 1. So I can rewrite this now. I could bring this 5 out front as a constant. So 5 times the integral of du over the square root of u. Okay, let's go ahead and write that left side down again. Well, what will that become? Well, I can rewrite my square root of u, which is on the denominator, as a rational exponent and bring them up to the numerator. So really I'm doing the integral of u to the negative 1/2 du. Okay, so that means I can add 1 to the power. So that'll be u to the 1/2, and then divide by that power of 1/2. And dividing by 1/2 is really multiplying by 2. So that means the 5 times the 2 will become a 10, u to the 1/2 plus c. And then I can go ahead and replace this u with my x squared minus 1. So let's go ahead and see what that looks like. So the ln, absolute value of y, equals 10 times, and it'll end up being the square root of x squared minus 1 plus c. Okay, so I have this plus c, and if this was going to be a general solution, at this point right now I would just solve for y by raising each side as a power of e, and I would be done. The problem is I have more information that I can use. I have this initial condition. So I know that my x value is 1, and my y value is e squared. So let's go ahead and plug those values into my equation the way it is right now and see what we have. Okay, so y was e squared and x was 1. So it looks like over here 1 squared is 1 and 1 minus 1 is 0, and square root of 0 is 0, and 10 times 0 is 0. So actually all that goes away. And the natural log of e squared, those are inverses, so I end up with 2 equals, well, c. So that was fairly painless. So now that I have that value of c, what can happen is I can go ahead and plug that in. So I have the natural log of the absolute value of y, and that equals 10 times the square root of x squared minus 1 plus 2. Okay? Well, at this point, we can actually solve for y to write my particular solution in explicit form. So let's go ahead and do that. I can do that by raising each side of my equation as a power of e. So the natural log and the e will cancel, and I have y equals, and so this will end up being e to the power of 10 times the square root of x squared minus 1 plus 2. So right here will be the particular solution and the final answer written in explicit form for my original separable differential equation with this initial condition. And before I finish this video, I want to take a look at two special examples here. And these are some expressions where it looks like the x and y variables are kind of jumbled together. And it looks like it might be hard or impossible to kind of separate them out. But when we're doing these separable differential equations, we need to be able to separate them or to detach them some way. So let's go ahead and look at this first one. We have e to the power of 2x minus y. So the x and the y are together as an exponent. So how can I kind of get these so they're not together as an exponent? Well, I can use a property of exponents which says if I have x to the m times x to the n, I have x to the m plus n. Which means I can decompose these, because you'll notice they have an m and an n together, and they got that way because I was multiplying like bases, so I added the exponents. So what I can do is say e to the 2x times e to the negative y, and in that manner I can separate these into two separate terms that are being multiplied together, and in that way I can detach my x from my y by using this property of exponents. Similarly, I have the square root of xy right here, so I could change this to rational exponents and say xy to the power of 1/2, and then by using my power rule here, I'm going to say it's x to the 1/2 times y to the 1/2, or I could say the square root of x times the square root of y, and here I have them divided as well. So there's just two little extra tricks there when you're solving these separable differential equations. Sometimes it might look a little difficult or a little strange to detach the x and the y from one another, but you can usually use properties of exponents or rational exponents to get the job done.